Now let us discuss that what are the various types of vibrations. We will characterize the vibration in your 5 parameters. First of all, let us discuss the first classification of vibration is on the basis of origination of vibration, right? On the basis of origination of vibration, how the vibration will be originated. So on the basis of your origination of the vibration is of 4 types. First one is the free vibration, forced vibration, self-excited vibration, and parametrically excited vibration. So first of all, let us discuss what do we mean by free vibration. Free vibration means the system, suppose this is a system, this system is at its equilibrium position right now. If I disturb this equilibrium position and leave the system, then the system will undergoing in the to and fro periodic motion because of its self energy, right? We can say that once the system is disturbed from its equilibrium position and then you leave it, then the system will be doing the to and fro periodic motion. Then we can say that that type of vibration is your free vibration. So we can say that in the free vibration, if I write, once a system is in this vibration, once the system is disturbed, you disturbed its equilibrium position and then leave it, and then you release the system, then it oscillates. Then this system oscillates about its mean position. Then it oscillates on its own without any disturbing force. Now there is no disturbing force acting on the system. Then it oscillates on its own without any disturbing force. There is no disturbing force acting on the system. It oscillates on its own. This system is known as, or this type of vibration is known as free vibration. For example, if we take an example of your pendulum, suppose this is a pendulum, this is some fixed link, and now here we have some pendulum. Suppose this is a pendulum and this is the equilibrium position of the pendulum, right? This is the equilibrium position of the pendulum. Now if I disturb the equilibrium position, I pull this up to this position, let us say, right? I disturb the equilibrium position of the pendulum and I take the pendulum at this position, and if I release this pendulum will oscillate like this. This pendulum will oscillate like this on its own without any disturbing force, right? This type of vibration is known as free vibration or natural vibration. This is also known as natural vibration, and in this case of free vibration, we are neglecting any type of damping, or you can say we are neglecting that there is no friction. In actual, what is the condition? This pendulum is surrounded with some surrounding air, right? At this point we have some solid friction, right? And the surrounding air will possess some of the friction to this ball, but we are neglecting all these kind of frictions. So we can say that this type of the vibration is known as free vibration or natural vibration, you can say. Another one is your forced vibration. In the forced vibration, the system is disturbed, or you can say the system is oscillated with the help of some dynamic force, right? You keep on applying the dynamic force on the system, and if that system is undergoing the oscillation, then that type of vibration is known as forced vibration, right? So we can say that in that forced vibration, your system is subjected to, in this case, the system is subjected to dynamic loading, right? Dynamic loading means that load which fluctuates with time. Dynamic loading. Dynamic loading means those loads which are fluctuates with time. Fluctuates with time. Then that type of vibration is known as forced vibration. That type of vibration is known as forced vibration. Also in the free vibration, if you are not neglecting the friction, I'll again explain, if you are not neglecting the friction, then it can be known as simple damped vibration, right? Free damped vibration. Free means there is no external force or there is no disturbing force, and damped means that some friction is present. In the forced vibration, we may consider the damping, we may consider the friction. So that vibration is forced damped vibration, right? Next one is your self-excited vibration. Self-excited vibration is neither your free vibration nor your forced vibration. They are not free or not forced vibration, right? Then this vibration is because of the system characteristic, right? Because of the system characteristic, these type of vibration will takes place because of some material characteristic and all. So that is your self-excited vibration. So we can say that self-excited vibration is not forced or free vibration. They are neither forced or free vibration. Not forced or free vibration. Then this is vibrated because of, if I write, this is vibrated because of system characteristics. Some of the system characteristics are such that they can make this vibration. System characteristics. That is your self-excited vibration. Next one is your parametrically excited vibration. In this parametrically excited vibration, one of the parameter of the system, right? We will discuss in our later discussion what are the various parameters of a vibrating system. So if I discuss here in brief that the parameters are your mass, stiffness, your some friction. So these three are the parameters of a you can say system, right? Or of a vibrating system. If one of the parameters are your undergoing vibration, suppose one of the parameter is your excited parameter, suppose stiffness, right? So in that case the vibration induced is your parametrically excited vibration. So in this case, if I can say that if suppose one of the parameter is dynamic, one of the parameter of the vibrating system is dynamic, then in that case the vibration induced is known as parametrically excited vibration, right? So in our course we will mostly deal with this free vibration. Free vibration will be of your, can say that if you consider the friction, then it is free damped vibration, and we will also discuss about this forced vibration. We are not that much consider this self-excited and parametrically excited vibration in our course. Our course is limited to these two types of vibration. Next classification, if we go about the vibrating system or the types of vibration, then the next classification, the second classification will be on the basis of nature of dissipation, how the energy will be dissipated, right? Suppose a pendulum is moving or oscillating, then this pendulum will have some energy, right? At its extreme position it has the potential energy, at its equilibrium position it has kinetic energy, and some mechanical energy is there with this system, with this pendulum system. So we have to discuss that what is the various types of means how the energy will be dissipated. The first one is undamped vibration. If there is no damping, undamped vibration, right? There is no damping, there is no friction. So in this case we can say the total mechanical energy will be constant. Total mechanical energy is constant. In this case there is no friction. Undamped means there is no friction. So in this case total mechanical energy is constant, right? So if there is no friction, no damping present, then obviously we can say that energy is conserved. So total mechanical energy will always be constant. It can change from kinetic to potential or potential to kinetic, but complete that total amount of mechanical energy will remain constant. and in this case the vibrations will be like this, right? It will be never ending process. If there is no vibrations, then we can say that the vibration will be like this. It will continuously moving and all, continuously moving, right? Because there is no friction, there is no dissipation of energy, energy will remain constant, so it will go on, right? This is your undamped vibration. Another one is your damped vibration. Damped vibration means we can say that in the damped vibration your energy is decreasing, or you can say energy is reducing. Energy is reducing. This is your damped vibration, and in reality we have, there is no condition that the friction is not present, right? So all the vibrations are your damped vibration. In reality energy is reducing, right? In reality all the vibrations are the damped vibration because friction will be there and energy will be reduced. So these type of vibrations will be like this. If I draw, then these type of vibrations will be like this, right? Its magnitude, its energy will decrease like this. Its magnitude and its energy will decrease as the vibrations will go on, as the oscillations will go on, and after some time complete vibrations will be damped, right? Complete this vibration will be damped, its magnitude will be 0. So this is your damped vibration. Damped vibration is of 3 types, right? Damped vibration is of 3 types. First one is your viscous damping. Viscous damping means, then in this viscous damping we have fluid friction, right? In this we have fluid friction. If the friction is present because of the fluid, then that type of damping is known as viscous damping. For example, this pendulum case, right? Suppose this is a pendulum, it is oscillating like this. The surrounding air will act as a fluid. It will exert some friction force on this pendulum. Then if you just disturb its equilibrium position, left it will start oscillating, and after some time you can feel that its energy will decreasing, and after some time it will remain at its equilibrium position. So this fluid, if I neglect the friction between this hinge and this thread, right? If I neglect this solid friction, then this is your viscous damping, because this fluid will exert some friction over there. So this is your fluid friction, and this is your viscous damping. Coulomb damping means when there is solid friction. If solid friction is present, then we can say that it is Coulomb damping. Right? So this is your solid friction, and in the material damping, the material will act as a damper, right? Suppose if there is some movement in the material, in the structure, suppose if any movement is there, right? It is oscillating, then in the material damping, that this is in the microscopic level, right? Grain boundaries, when the grain boundaries will move, when the crystal structure will move, it will exert some friction force, and that type of damping is known as material damping. So in our course we will deal with this viscous damping and Coulomb damping only. We are not going with the material damping. So this is the second type of classification on the basis of dissipation of energy. The third classification is on the basis of nature of vibrating system, how the vibrating system is. So there are 3 types. One is the single degree of freedom system. Single degree of freedom system means only one parameter is required to define the position or the state of the system. That is single degree of freedom. Another one is the multi-degree of freedom system. If more than one parameter is required to define the state of the system, then we can say multi-degree of freedom system. The third one is your infinite degree of freedom system. If the parameters which is required is infinite, if it is infinite, then it is known as infinite degree of freedom system. And this type of vibration is basically with the elastic bodies. It is basically with the elastic bodies. Elastic bodies, right? As we already discussed the case of your cantilever beam. In the cantilever beam, each and every molecule or atom of the cantilever beam, each and every point on the cantilever beam is under its vibration, right, like this. So that is your your infinite degree of freedom system, right. So in order to specify the position of the complete cantilever beam, we want to know each and every point, the condition of each and every point. So that is your infinite degree of freedom system, right. In our course for the GATE, only this single degree of freedom system is in our syllabus. So we will only consider the single degree of freedom system. Another classification is on the basis of vibration type, right. Another classification is on the basis of vibration type. On the basis of vibration type, we have three types of vibrations. One is the harmonic vibrations, another one is the periodic but not harmonic, and another one is the random vibration. Harmonic vibrations means like of sine function, cosine function, right. They are the harmonic functions. Harmonic functions means sine function or your cosine functions. So if your function or the vibrating system is a function of your sine or cosine, then we can say that it is your harmonic function. And the vibrations will be like this, sine curve or cosine curve, like this. This is your harmonic function. So another is your periodic but not harmonic, right. The vibration is periodic, or you can say that the oscillation is periodic, not vibration. Oscillation is periodic. Periodic means it can repeat itself after some time period, right. That is known as time period of the oscillation. After a fixed interval of time, if the motion will repeat itself, then it is known as periodic motion, right. After some period it is repeating itself, it is periodic motion, but that is not a function of sine or cosine. That is known as periodic but not harmonic. That is also a type of vibrations, periodic. For the vibration, the most important thing is periodic, that has to repeat after itself after some constant period of time. So we can say that that is your periodic motions. So in this case, the motion is periodic, or the oscillations are periodic but not harmonic. They are not harmonic. They are not a function of sine theta or cosine theta. So for example, the motion will be like this, or better I can write, right. Suppose these type of vibrations are periodic, right. After this it itself repeat, then it repeat itself, right. This is a period of time or time period, right. After this time period it will repeat itself like this. These are the periodic vibrations but not harmonic. They are not the function of sine theta or cosine theta. Another one is the random vibration, when the vibrations or the oscillations are random, right. Suppose like this, suppose something like this. They are the random vibrations, right. They are not repeating itself after some time. So we can say that these are the three types of the vibrations: harmonic, periodic but not harmonic, and random vibration. Another type of vibrating system is, or another classification is based on the system parameter characteristics. System parameter characteristic means we have some what is the parameter of the vibrating system? We can say that is a mass, stiffness and friction, right, or you can say damping. So if the system parameters are linear, if the spring is a linear spring, then and all the system parameters are linear, then the vibration induced will be the linear vibration. Linear vibration means all the parameters of the system of the vibrating system are linear parameters, and if the parameters are not linear, then we have non-linear vibration. So in our study we are basically concerned with the linear vibrations. We always consider that the spring which we have is a linear spring, or you can say the stiffness is a linear stiffness. So that is your type of the vibrations. So these are the basic classifications of the vibrations, just to an overview of the vibrating systems, how many types of vibrations are there. So we will start with the very basic, that is a free vibration. And before that, before starting the vibrations, first of all let us discuss about the basic parameters of a vibrating system. What is the basic requirement of a vibrating system. We will discuss first, then we will go with the natural vibration or free vibration, right?